Hello students, we have seen up till now two of the main units of engineering mathematics 2 in unit number 6. Now we are going to learn multiple integrals and their applications. Content of this presentation: double integrations, evaluation of double integration, example when the limits are provided. Double integration. A double integral is defined as a limit of a sum. Let f of xy be a continuous function of two independent variables x and y defined in a simple closed region R. Subdivide R into elemental areas delta A1, delta A2, delta A3, so on up to delta AI. By drawing lines parallel to coordinate axis, we get the required figure in the next part. So this is the figure. This is a function of x and y. Then this becomes a closed region, simple closed region R, and this is an elemental area delta AI. So we have taken a point xi yi at this elemental area delta AI. Then this is a function of x and y. Therefore, you are having this form of the figure. Let xi yi be any point in delta ai. Again, we have taken a point xi yi in this elemental area delta ai. Then find the sum f of x1 y1 delta a1 plus f of x2 y2 delta a2 plus and so on. So these are the functional values at the point x1 y1, and this is the elemental area at the point x1 y1. Then this is f of x2 y2 and delta y2. So this is f of, this is summation up to f of xn yn multiplied by delta an is equal to this summation. You can write in the form of, this is sigma, this is summation I is equal to 1 to n f of xi yi delta ai. Now increase the number of subdivisions infinitely large, that is as n tends to infinity, so that delta ai tends to 0. In this limit, if the sum exists, that is delta ai tends to 0 of the summation I is equal to 1 to n, limit of this as n tends to infinity, f of xi yi delta ai exists, then it is called double integral of f of xy over the region of R, and it is denoted by this the double integral along the region R of the function f of xy dx dy. So this is a notation for a double integral of a function of two variables. Then note that the continuity of f of xy is a sufficient condition for the existence of double integral, but not necessary. The double integral exists even if finite number of discontinuous points are there in the region R, but f should be bounded function in that case. You'll have to get the evaluation of the double integral. In practice, a double integral is computed by repeated single variable integration. Integrate with respect to one variable, treating the other variable as a constant. So this evaluation of a double integral is, a double integral is computed by repeated single variable integration. That means A double integral is evaluated like a single integral with respect to one variable, keeping the other variable constant or treating the other variable as a constant. Then here we take three cases where case number one, if the region R is a rectangle given by R is equal to a function of x and y such that x lies between A and B, y lies between C and D, where A, B, C, D are constants. That is, the region R is like a rectangle. Then the evaluation of this double integral along the region R, which is a rectangular region, f of xy dx is equal to integration from C to D, integral from A to B, f of xy dx and then a dy. That means f of xy is integrated with respect to x between the limits a and b. Then the value is integrated with respect to y between the limits c and d. That is, if the limits are constants, the order of integration is immaterial, provided proper limits are taken and f of xy is bounded in the region R. So here, this is the region R, where this is a rectangular region. Here you are having, it is having x varies from x is equal to a to x is equal to b, and y varies from y is equal to c to y is equal to d. So therefore, these are constant integrals, or the limits are constants. Therefore, the order of integration is immaterial. Either you can integrate with respect to x between the limits x is equal to a to x is equal to b, or you can integrate with respect to y between the limits y is equal to c to y is equal to d. So this is case number one. Then case number two. If the region R is given by R is equal to a function of x and y such that x lies between a and b and y lies between the curves, that is g of x is less than or equal to y is less than or equal to h of x, where a and b are constants. Then this evaluation of a double integral of f of xy dx dy over the region R is given by integration from a to b of the integration of f of xy dy g of x and h of x. So this integration f of xy dy is evaluated with respect to y first. That is, when you integrate this with respect to y, the limits for y are functions of x. Then when you put these functions of x in the variable y, then this function will get converted to a function of x. Then that function of x has to be integrated between the constants limits x, that is a and b. So this is a variable limit. This is a curve. That is, you are taking a strip. So in the next figure, I will show you. Here, the limits of x are constants. That is, x is equal to a and x is equal to b. Then you are first integrating with respect to y. Then you are taking a strip, for example, the lower end of it lies on the curve g of x, and then the upper end of it lies on the curve y is equal to h of x. So therefore, when you are integrating with respect to y, you are taking a strip parallel to y-axis. The lower end depends on, or the lower end lies on y is equal to g of x, the lower limit of y, and the upper limit of it lies on y is equal to h of x. Okay, so therefore first you are integrating with respect to y, and then you are integrating with respect to x. Here the limits of x are constants and the limits of y are functions of x. So h of x and g of x are the functions of x. So we integrate first with respect to y and then with respect to x. Here, the order of integration is first y, then x. Okay. Then in the case number 3, the next case, what is that? If the region R is given by R is equal to a function of x and y, where x lies between g of y and h of y. Now these are the functions of y. X is a function of y and y is having a constant limits c less than or equal to y less than or equal to d, where c and d are constants. Then the evaluation of a double integral f of xy dx dy over the region R is equal to, first you are integrating with respect to x. These are the variable limits. Variable limits, you are taking a strip parallel to x-axis. Then you are integrating this f of xy with respect to x between the limits g of y to h of y. And then you are integrating with respect to y between the constant limits c and d. So order of integration in this case is first x and then y. Here the limits of x are functions of y. So we integrate first with respect to x and then with respect to y. So that is, this is a strip parallel to x-axis because you are integrating with respect to x first. The lower end of it lies on x is equal to g of y and the upper end lies on that x is equal to h of y. You are taking a strip parallel to x-axis first. Then to cover this region between this curve are these two curves and these two straight lines. We roll this PQ parallel to itself from the point y is equal to C to y is equal to D. So the entire region is covered. Here the order of integration is first with respect to x and then with respect to y. Okay, so these are the three cases where you are evaluating the double integral. Then you'll have to note this. What is that? When the variable limits are involved, we have to integrate first with respect to the variable having variable limits and then with respect to the variables having constant limits. That means when you are having x is a function of h of y and g of y, for example, then first integrate with respect to that with respect to x, keeping y constant, and then integrate with respect to the constant variables or variables having a constant limits. When the limits are constant, the order of dx and dy determine the limits of the variables. Then we'll see some of the examples. Then it becomes clear to get the idea how to evaluate the integrals. That is a double integrals. For example, evaluate integration from 0 to 1, integration from 1 to 2, x into bracket x plus y dy dx. So the if you see these constants, so this is equal to a, this is equal to b, this is equal to c, this is equal to d. Here either these are the constants, therefore you are integrating with respect to y or with respect to a immaterial of the order of the integration. So how to start this? So we'll take the solution. Let I is equal to the given integral from 0 to 1, 1 to 2, x into x plus y dy dx. Now this you can write. How you can write? Integration from 0 to 1. This is inside the bracket. Integration from 1 to 2, x into bracket x plus y dy dx. That means the inside integral is integrated with respect to y, keeping x constant, and then this whatever you get, that is integrated with respect to x between 0 and 1, the meaning of this bracket. Then here with respect to y, x is constant, so therefore x is taken outside. Then the integral of x with respect to y, becomes integral of dy is equal to y. Then integral of y with respect to y is equal to y square upon 2. What are the limits? 1 to 2. So the lower limit is 1, upper limit is equal to 2. Then whatever the value you get, it has to be integrated with respect to x. So therefore, this becomes integration from 0 to 1. This is x. Upper limit is 2. 2, that y is equal to 2. So 2 into x becomes x into 2 or 2 into x. Both of them are same. Then plus this becomes 2 square. 2 square is 4. 4 upon 2. 4 upon 2 is equal to 2. So therefore, this 2 has come directly. I have put that y is equal to 2. 2 square is 4. 4 upon 2 is equal to 2 as far as the upper limit is concerned. Then the lower limit with y is equal to 1. When y is equal to 1 with a lower limit, this becomes that y is equal to 1. This becomes minus 1. Minus 1 multiplied by x is minus x. Then this y is equal to 1 becomes equal to minus 1 upon 2. Okay. And then this has to be integrated with respect to x again. Then simplify this. That's equal to 2x minus x is equal to x. Okay. So therefore, this is 2x and minus x is equal to x. Then this is equal to 2 minus half is equal to plus 3 by 2 into x. So that's equal to integration from 0 to 1 x into bracket x plus 3 by 2 into dx. That's equal to integration. This is x into x is x square. Then this is 3x upon 2 into dx. Then integral of this x square is x cube upon 3. Integral of 3x upon 2 is equal to 3x square upon 2 into 2 becomes 4. Then between the limits 0 to 1. Put the upper limit x is equal to 1 and the lower limit x is equal to 0. When you put the upper limit x is equal to 1, the first part is 1 by 3. The second part is 3 by 4. When you put the lower limit x is equal to 0, this is also equal to 0. Therefore, the lower limit is equal to 0. Then we get this is 1 by 3 plus 3 by 4. Again, take the LCM. So this becomes that's equal to 4 and this becomes a 9. 9 plus 4 is 13 and 3 into 4 is 12. So therefore, 13 upon 12 is the value for the double integral from 0 to 1, 1 to 2, x into bracket x plus y dy dx. That is evaluation of a double integral when both the limits are constants. So here the example we are seeing when the limits are provided, limits are given to you, then you are finding the double integrals. Then we'll take the next question. This is the example when the limits are provided. The question number 2, integration from 0 to 1, integral from 0 to 1, that is the double integral dx dy square root of dx dy divided by square root of 1 minus x square root of 1 minus y square. Now again, as far as the solution of this double integral is concerned, we take let I is equal to the given integral. Okay, that is 0 to 1. Then integral from 0 to 1 divided by this is dx dy divided by root of 1 minus x square root of 1 minus y square. Here, these, if you see the functions, these are independent of x and y. That means you can put root of 1 minus x square as one function of x and root of 1 minus y square as another function of y. Then the limits are also same. Therefore, you can put this as integral from 0 to 1 dx upon root of 1 minus x square and integral from 0 to 1 dy upon root of 1 minus y squared. So these two are, again you'll have to apply the formula of integral of dx upon root of 1 minus x square is equal to sine square x between the limits 0 to 1, and this is dy upon under root of 1 minus y square is sine inverse y between the limits 0 to 1. Then put the upper limit and lower limit. Sine inverse of 1 minus sine inverse of 0 in one bracket. In the other bracket, sine inverse of 1 minus sine inverse of 0. Then sine inverse of 1 is pi by 2. Sin inverse of 0 is equal to 0. So from the first term, you get pi by 2. Similarly, from the second term, you get sin inverse of 1 is equal to pi by 2 and sin inverse of 0 is equal to 0. So therefore, this becomes pi into pi is pi square and 2 into 2 is equal to 4. So therefore, pi square upon 4 is the evaluation of the double integral 0 to 1 integral 0 to 1 dx dy divided by root of 1 minus x square and root of 1 minus y square. Then we'll take another example so that you can get the idea and you can just go on finding the evaluation of the double integrals when the limits are given. So this is the last example of this type when the limits are provided. When the limits are provided, evaluate integration from 0 to a, integration from 0 to a square root of a square minus x square y dx dy. Now, if you see this, the limits are provided. These are the functions of x. So when these are the functions of x, first we'll have to integrate with respect to y. And then x square becomes constant, you can take it outside because these are the functions of x. If these are the functions of x, integrate first with respect to y and then with respect to x. That you'll have to understand by the given order of integration and the given limits. So we'll start with solution. Let I is equal to this value. The double integration 0 to a, then 0 to root of a square minus x square y dx dy. Then I said these are the functions of x. Therefore, you'll have to integrate with respect to y. That means you are taking a strip parallel to y axis. So therefore, when you get this x square becomes outside, we can take it outside. Then you can write integral from 0 to a x square into bracket integral from 0 to root of a square minus x square y into dy. That means you are integrating y with respect to y first and then integration with respect to x. So this is equal to 0 to a, then this is x square as it is, y integral is y square upon 2 between the limits 0 to root of a square minus x square and then dx is equal to this 1 by 2, you can take it outside, integral from 0 to a, this is x square, then you are putting the upper limit is root of a square minus x square, this is y square already. So when you put this square root of this value, square root will get cancelled, therefore I get a square minus x square. When you put the lower limit, y is equal to 0, that's equal to 0, so that value we have not written here, so automatically the lower limit is equal to 0, therefore only the upper limit exists and that upper limit is a square minus x square into dx. So therefore this is equal to, now take this x square inside, you get x square a square, then x square into x, the square is equal to x to the power 4 into dx. This is 1 by 2 integration from 0 to a x square into a square minus x raised to 4 into dx. So again you'll have to integrate this with respect to x now. This is 1 by 2, then this is a square is constant, then x square integral is x cube upon 3, then minus x to the power 4 integral is x to the power 5 divided by 5 between the limits 0 to a, that is from 0 to a. Upper limit is a, lower limit is 0, put in the form of that. This is 1 by 2 a square, this is constant, a x is equal to a becomes a cube upon 3, then you'll be having this is minus, then this is x to the power 5 upon 5 you are having, x is replaced by a, the upper limit, so therefore this becomes minus of a to the power 5 upon 5, then the lower limit is minus of 0 and the other part is also minus of 0, so therefore 1 upon 2, then you are having 2 a to the power, this is a to the power 5 and a to the power 5, then this is equal to, take the LCM, that becomes 15, so therefore 2a to the power 5 upon 15, then this 2 and 2 will get cancelled, this becomes a to the power 5 upon 15. So these are the examples on the double integral when the limits are provided. So in the next lecture, I'll go for the problems when the limits are not given, only the region of integration is given, and then we'll have to first find the limits and then you'll have to evaluate. So up to that, thank you.